In electric circuits, basically what your electric currents and electric circuits. Okay. The first thing is, what is current? You know it. Recollect all the definitions. What is current? Rate of flow of charge. Very good. Delta Q over delta T. And current is measured in amperes. Charge is measured in coulombs, and time is measured in seconds. So that is a unit connection to that definition. And to give an example of that, if through a wire there is a current of 5 amperes, and if it flows for a time of 3 minutes, how many coulombs are actually going to run through it? How many coulombs will run through the wire? So what you do is pick that equation. I is equal to Q over, so I can simplify and write I is equal to Q over T. So the Q that is running through is IT. The charge that is running through is IT. So then put the current on. The current is 5 amperes, and the time is 180 seconds. So you get 900 ampere second. See, ampere second, which is the same as coulomb. So 900 coulombs are actually going through this wire, one spot on the wire, every 3 minutes. 900 coulombs. You know what is a coulomb? How many electrons are there in a coulomb? 6.25, good. 6.25 times 10 power 18 electrons. So if 1 coulomb is that many electrons, 900 coulombs is going to be a lot of electrons. Okay? And all those electrons are passing through this wire in 3 minutes, just for a current of 5 amperes. Is that clear? So this is something that you have done last year, connection between this and this. So what is a coulomb? A coulomb is ampere second. Remember, coulomb is a derived SI unit of charge. This is a basic SI unit of current, and this is a basic SI unit of time. So ampere second is coulomb. So these are the basic units. These are the derived units. And then you have seen the electric battery. What is a cell or what is a battery? It's a chemical generator. So this is a chemical generator. You got electrodes and you got an electrolyte, and it's a chemical generator. And this chemical generator has what we say as EMF. Remember last year? Electromotive force. So this one has electromotive force, and that is what is marked here as 1.5 volts. This is 1.5 volts EMF, not potential difference. But if I use a meter and measure how much is the voltage here, then that is potential difference. So understand the difference between EMF and potential. EMF is its maximum capacity of delivering charges. So this is EMF, and I'll go through the definitions of EMF later. That is, this is called the D cell. Every cell has got names. So that's a D cell. This is a double A, also 1.5 volts, capable of not sending too much current and so on. Yeah.
For cells, do we have to know the chemical reactions?
No, you don't have to go into details of chemical reactions. You don't have to know what the electrodes are. Actually, the electrodes are zinc on the outside and carbon rod inside. And the electrolyte is ammonium chloride in the jelly form. And of course, they put other stuff to prevent oxidations and all that. So this is basically an alkaline cell. That's why it's called an alkaline cell, because it is ammonium chloride inside. Now this is a C cell, also 1.5 volts. That is C. Double A. This is triple A. You are familiar with that. Triple A, and it's also 1.5 volts. And you know what this one is? This is how many volts? 9 volt. Now you call it 9 volt battery. This is called a 9 volt battery. Why? Because it's not one cell, it is 6 cells inside. And the 6 cells are put together, and that is why it's giving us 9 volts. So this is 9 volts because it's a pack of 6 cells. That's why this is called a battery. These are not called batteries. Those are called cells. This is a battery, and there's 9 volts. The number of this one is like 23A. That's the name for this. How many volts is this approximately? How many volts? 12 volts. 12. Looks pretty small. This is also a battery. It's not one cell. It's 12 volts, which means how many cells? 8 cells. 8 times 1.5 is 12. So there are 8 cells in it, small things together. This is what is in your garage door opener and all that. So if your garage door opener is not working, pull out this and then go and buy that number 23A. Kind of expensive too, but yeah, you can get it for $3-4. So that is the one which is supposed to be in most of the remote controlled stuff. That's 23A. And there is another cell. This is AAA. Have you seen a 4As? There are some with 4As, and that will be kind of taller than this, and skinnier. So they're used in different purposes. So those are cells. Now what you have to know about cells is something that we will do throughout. Like cells, it has an EMF. Okay? A cell has an EMF. And then you should also know this, that a current flows. So when you have a cell, and when you connect it to a light bulb or something, when you connect it to a light bulb, which way are the electrons moving? Yeah, from here, electrons are going to go like this. Electrons are going to go like that. But we say the conventional current is which way? The conventional current is opposite to the direction of flow of electrons. The conventional current, what you normally write as I, is this one, which is opposite to the direction of flow of electron. So a conventional current is actually opposite to the direction of flow of electrons or in the direction of flow of positive ions. Okay? But in a metal wire, there is no positive ion, so we can't talk about it. And then the other thing that you have gone through is Ohm's law. You have done Ohm's law, right? And now what is Ohm's law? Ohm's law is actually telling you, all right, here's a current that is flowing in. When you connect a voltmeter here across this point, this potential difference here will be V. The potential difference will be V between these 2 points. Where is the potential supposed to be higher? This side or this side? Where is the potential higher? This side. Yeah. Think of yourself like, think of a running race. A race, and this is a track. Where do you have more energy, before the race or after the race? So before the race you have more potential, after the race you have less energy. So there is a potential difference created. And the potential difference depends on I. Why? Because imagine one person is running the race. How much energy is going to use? Drop a certain amount. Imagine 10 people are running the race, and each one is going to lose the same amount of energy, so which means the cumulative total energy is going to be more, right? So V is proportional to I, and that is your Ohm's law. That is your Ohm's law. V is proportional to I, and something you have done last year. And since V is proportional to I, V is equal to IR, where R is called resistance of whatever device you're talking about. In this case, it's a light bulb. So R is the resistance of the light bulb. So what is R? R is equal to V over I. R is simply the ratio of the potential difference to the current. Now, what is the unit of potential difference over current? What is the unit of V? Volts. What's the unit of this? Amperes. Now, this is a basic unit, understandable, but this is not a basic unit. Volt is a derived unit. How do you split that up into basics? Volt. What is a volt? Any other formula for replacing volt? What is a volt? Joule over coulomb. How much work is done per coulomb? So it is like joule per coulomb. And then this A. As you can see here, coulomb is also a derived unit. Joule is also another derived unit. So I need to break all of them out. What is joule? Newton meter? Newton meter is joule. This coulomb is ampere second, and then there is an ampere. Now, Newton is also a derived unit, so break it down. What is Newton? F is equal to ma. So this becomes kilogram mass times acceleration, times meter over ampere square second. Now, everything is basic. You have to just rearrange it. If you rearrange it, you get kilogram meter square second to the power of -3 ampere to the power of -2. That is the SI base units of resistance. And instead of writing all this, we call it ohm. We call it just ohm. So how much is the resistance? Instead of saying 50 kilogram meter square second to the power of -3 and ampere to the power of -2, instead of saying all that, we just simply call it ohm. That's basically enough. And how do you write it symbolically? It's omega. Omega is a symbol for ohms. Okay? So we'll just say, all right, 57 ohms. So the last one we touched upon was Ohm's law, and you know everything about Ohm's law. V equal to IR. Right? Since you've done this last year, it should be just a recollection. So Ohm's law is clear. V is proportional to I. Now if you sketch a graph of V on the y-axis and I on the x-axis, you are expected to get a straight line, right? Indicating that V is proportional to I. So on that straight line, V is proportional to I. And a material that behaves like this is called an ohmic conductor. A material that behaves like that is called ohmic conductor. Which also means that there are non-ohmic conductors. There are different conductors which are non-ohmic. That means when a current passes through that material, its resistance is not going to stay the same. So we saw this, that the slope of this line, slope, gives resistance, right? Now why we say this is an ohmic conductor is because the resistance is unchanged. The slope of this line stays the same. Now remember, when you do a test or a homework, just make sure that this is V and this is I, and then the slope is the resistance. If this is I and that is V, it is not resistance. It's reciprocal of resistance. Make sense? Mm-hmm. So the steeper the line on this one, it's going to be more and more resistance. But if it's a graph the other way around, that will be more resistance. Okay, it's inverse. So slope gives resistance over here. And when it is a non-ohmic conductor, what is a non-ohmic conductor? A conductor that has its resistance changing with current. So that is a non-ohmic conductor. Why we say it's non-ohmic? Because it doesn't obey the law, the Ohm's law. The Ohm's law is V is proportional to I, which means the resistor is constant. Constant slope, constant resistance. But this one is a non-ohmic conductor, which does not have a constant resistance. The resistance initially is the slope of this line, which is low. And see what happens to the slope as it goes on. Slope is increasing. Did I mention this last class? No. Okay, slope is increasing as we go on. That means for greater and greater currents, the slope is increasing, which means the resistance is increasing. So the opposition to the flow of this current is going to increase as the current starts increasing. That's what you see here. Resistance is increasing continuously. The slope is increasing. Now, such a material where the more you push the current, the more the resistance increases, is a metal. Any metals will behave that way. Any metal will behave in this manner. Now, why is the resistance increasing in a metal when you push more current into it? And what is current? If you understand that, you'll know it. What is current? Flow of electrons. When electrons flow, they don't have a straight path to flow. They always bump into stationary atoms, right? So electrons through a wire is not something that goes in a straight line. So it goes bumping into atoms. Like, for example, if I have to go to that place, see, something is attracting next to the window for me. All right? So what I do is, I want to go there. I'm attracted by a potential difference. I'm the electron. I'm attracted by a positive potential over there. And so what will happen is, I'm experiencing a force. What force is that? F is equal to? Formula? Q E. So I experience a force QE towards that side. And so depending upon my mass, I will have what? Acceleration, which will cause me to speed up. So what will happen, as soon as I have that attraction coming in, I will start like accelerating, and then suddenly I bump into the table. When I bump into the table, what I'm doing is I'm surrendering all my kinetic energy to the table. I'm passing the energy to the table, and I'm stopped. But nothing can stop me. I have to go there. So I start making my next move, and I'm trying to bump in everywhere. All the atoms, I'm bumping into each other. I go here, I hit him. I pass my kinetic energy to him, and he gets agitated. Understand the words? This atom is getting agitated, angry. And then after that, I go here, agitate him. And finally, I reach my goal. I'm there at the window. But while I did this, I caused agitation to some of these atoms, and that agitation of atoms is what produces heat. Heat. So the agitation is producing heat. So when a current flows through a wire, heating is a consequence. You cannot avoid it. Heating is going to be there. Now, how small is the heating effect? And all that will be dealt with later on. But right now, Ethan, wake up. All right, so electrons, when they bump into atoms, they agitate the atoms, make the atoms vibrate faster, which means the temperature of the material increases. And that causes more obstruction to the flow of electrons. If you are absolutely quiet, sitting like this without any problems at all, sleeping in the class, I can just sneak through you, through all the gaps possible, and I reach there without disturbing anybody. So I have easy flow, no opposition. And imagine you ate ice creams or chocolates and all that during lunch, and you came and sat here. You're hyper. You're kicking your legs and swinging your hands, and now if I try to sneak through you, I'll get hit many times. I won't be able to go to the other side. I will have to overcome a lot of opposition, which is resistance. So why is the resistance of a metal increasing when electrons try to flow through the material? When a current flows through material, why is the resistance increasing? Simple answer. When a current flows through a material, electrons bump into the stationary atoms, creating heat, creating agitation. And agitated atoms oppose the flow of electrons more than the other ones. So if there is less agitation, resistance is small. If there is less agitation, resistance is small. If there is more agitation because more current is trying to disturb those atoms, then resistance is getting increased, right? So as I increases in metals, as I increases, resistance increases. That's in a metal. Well, that's also non-ohmic. It's non-ohmic. Well, this one, V is proportional to I. I just mentioned that if there is a flow, you're going to have heat as a consequence, right? Then how come you have an ohmic conductor where V is proportional to I? Resistance is constant. How can that happen? How can that happen? According to what I just now said, it should be a consequence of current is going to be heat. That is no excuse about it. No escape about it. It is just going to be happening because atoms are there to obstruct the flow of electrons. And so this agitation is going to be there. But how come I drew a straight line and said resistance is constant and that is Ohm's law and that is an ohmic conductor? And I'm saying this is non-ohmic. In fact, there is nothing that is ohmic conductor. There is nothing that is an ohmic conductor. You can't call anything as ohmic conductor. Every conductor will have consequences of current flowing through it. So when I have a wire, okay, if I have a wire and if a current is passing through this wire will warm up. That is an immediate consequence. But sometimes you don't feel that warming up, right? You don't feel the heating effect. Why? Sometimes you don't feel the heating effect, and sometimes you do feel the heating effect. Sometimes the heat can be enough to burn you. Okay? So what is controlling it is the current itself. If the current is pretty small, if the current itself is very small, you know the heating effect depends on I square R, the power, right? You've done it last year, that's why I'm like really talking about it. If you've forgotten the power concepts, I will explain to you the power concepts right away. Let's go to power now. To go to the basics of power, let's go to work done. What did you learn in chapter 17 about work done? When you move charge Q through a potential difference V, what is the work done? QV. So you got the foundation there. Now dividing both sides by time. Dividing both sides by time. What do you get here? Power. And what do you get here? Q over T? Current. So that's your power equation. In electricity, power dissipated or power used up depends on current and voltage. So for example, if that television is 100 watts, if the television is 100 watts, and if the voltage it's operating on is 120, which is nearly right. So 100 watts is equal to I times 120. So what's the current that this television is drawing? It's 10 over, so it is 0.83 amperes, is it? 0.83 amperes is the current that's actually flowing through the wires connecting it to the power supply. We can say it straight away from here. I know it's operating on 120. I know it's 100 watt because the label is there. So I know how much current it is drawing. So when you know the current is drawing, can you figure out the resistance? You know V is equal to IR. Can you figure out the resistance? You can figure out the resistance by many ways, but I'm just showing you that yes, you know the voltage, you know the resistance, I mean the current now, so you can figure out the resistance. How much is it? So what is R? How many ohms?
144.
144 ohms. That's the resistance of that television. The television is offering that much resistance or opposition. When you plug the wires in, the current is going through that device and the whole device offers that much opposition, 144 ohms. And if the current is going to stay steady and if the voltage applied is steady, then the resistance should nearly be the same. Okay? Now look at this equation once again. If I substitute Ohm's law, V equal to IR right here, if I substitute that over here, what do you get? Power is equal to I square R. And if I substitute I as V over R, again from the Ohm's law, we get power is equal to V squared over R. So all these are important equations. They're all for power. You can use any of those equations. So if I asked you what's the resistance of the television, straight away, you can use this equation. Power is 100 watts. Voltage is 120 volts over resistance. Can you find that out? Cross multiply, and you'll see it's 144. You can use any equation literally to get there. So in this when you use this equation, you don't care about the current. Previously, you used the value of current to get the resistance, but you can use this straight away. Got it? Okay. So coming back to this equation, is that all clear? Now coming back to these equations, this is an equation that actually kind of helps you very clearly to find out how much is the power dissipated through a resistor when you know there is a current flowing through. So if a current is flowing through here, and that is 0.83 amperes square times 144 ohms, okay, what is the power? You already know the value, so that's what you're going to get. So power is equal to 100 watts. Okay. Power is equal to 100 watts. So you know the power, the rate of energy dissipation is 100 watts. That means what? 100 joules it is spitting out every second in the form of light, heat, mostly heat. You know, light and heat and sound, everything together. So when a television is on, you get light, heat, and sound. All the forms of energy that is actually coming out from there is this. Not just the light, not just the heat coming from the back, not just the sound that's coming out. It's all combined together. The sound is probably 10 watts. The heat is probably around 70 watts. And probably the light part of it is 20 watts. Different proportions. But this is the total power. Now, this power means a lot. That's why it's heating up. So when the television is not working, you can feel there's nothing at all. But as it works, you can see that it is like getting hot, right? If the current is very small, there will be a significant difference in this. So suppose the current is very small, not as much as this. Suppose the current is only 0.01 amperes, which is basically 10 milliamperes. If the current is 10 milliamperes, something that normally flows through an adapter or phone chargers, like small currents. It's not too much. 10 milliamperes, which is 0.01 amperes. If that is flowing through the television for some reason, let's say, what is the television's resistance? 144, right? What's the power dissipation? The power dissipation is going to be pretty small, very small. You can calculate that yourself. How much?
14 milliwatts.
14 milliwatts. Yep, 14 milliwatts. That is the power dissipated, which is 0.0144 watts, which is very small. Will that be sensed by human hands? No, it's too small. This power is very small. Whereas if the current is 1 ampere, through the same thing, that will produce a lot of heat. 100 watt is a lot. 100 watts is a lot. A 100 watt bulb is a lot of heat and light. You touch the bulb when it's operating, you'll feel it. 100 watts is a lot. So when the current is 1 ampere, through the same thing, the power will be 144 watts. And look at this one now. When the current is like 1/100th of an ampere, it is only 14 milliwatts, which is negligibly small. So when a device takes a very small current, the heat that it is going to generate is so small that as the heat is generated, it will just sneak out into the atmosphere very easily. It won't accumulate there. It won't accumulate because it's kind of going off. And in this situation, you can see very clearly that the resistance will stay constant because temperature is constant. So if you can maintain the temperature constant, you got the Ohm's law, ohmic conductor. If you can maintain the temperature constant by cooling or whatever you want to do, you do, and then you get ohmic conductor. If you cannot maintain the temperature constant, then that is where it actually changes to a non-ohmic shape. So small devices like, you have an electronic watch and you put a battery in it, and the current that's flowing is like in microamperes. The current that's flowing from the battery through the circuitry is only microamperes. So what if you square the microamperes in terms of resistance? It's going to be insignificant. You get it? And that's why you don't feel the watch warming up. You don't feel it warming up. The watch will stay cool, even though there's a current flowing through. Why? Because the current is too small, and so heating effect is impossible to think of, and in such cases, Ohm's law is definitely true. So if I have a resistor, and if I pass a very small current, will the temperature of the resistor stay nearly the same? Yes. But if I take the same resistor and pass more current into it, it's possible that the resistor starts warming up, heating up. Okay? All right. So coming back to this now, so you understood about power, at least you've gone through the power concepts. Don't forget those equations, those are important, very, very important. Now, this is metal. In a metal, the temperature is not going to stay constant, it's going to increase. It's going to increase. So in an incandescent bulb, a normal bulb, is, you know what an incandescent bulb is? It's a filament, like your headlight. Okay, not the LED. Incandescent, which means like you have the filament down. If you have an incandescent filament lamp, its resistance, if you check the resistance before you turn it on, is actually small. Yes. It is small. And then when you turn it on, it's going up to 2000 Kelvin. You know, the filament itself is going up to 2000 Kelvin. You don't feel that because it's only the inside part. The bulb will feel hot, but it is not going to reflect 2000 Kelvin. 2000 Kelvin is the temperature of that filament. That's what makes it almost white. By the way, if the filament lamp is 2000 Kelvin, what do you think is the sun's temperature? Surface temperature of the sun?
At least 10.
At least what?
10.
10 Kelvin?
At least.
10 Kelvin?
That's very
That is very, it's always going to be true. By the way, the room temperature is 300 Kelvin. So now you're talking about sun's temperature. What is it? If the light bulb's temperature is 2000 Kelvin, the filament, approximately 6000 Kelvin. That's all. So, well, it is a concentrated heat that is dissipated from that little wire. That's what causes it. Do you get it? So 2000 Kelvin is the filament temperature, and that is why the resistance actually increases. So when a light bulb is operating, the operating resistance is actually higher than the real resistance when it is cold. Say, for example, if you take your, the floodlight which is kept in your house somewhere, right? So if it is a 200 watt floodlight, and you're going to operate it on 120 volts, If you're operating on 120 or 110 volts, 2000 watts, what's the resistance of that? How do you find the resistance of that floodlight bulb? So you go to which formula? Power and voltage and resistance. So without current, V square over R is equal to power, so you can use that. And so the question is resistance. So resistance is equal to V square over power, and that is 120 square over 200. That is 72 ohms. Well, that is when it is operating. When it is cold, when the bulb is like not working, check its resistance. It may be like 5-6 ohms. It won't be too high. It'll be like 5-6 ohms. And when it turns on, that is the resistance. Okay. Well, we'll talk about that later also. You get it? Now coming back to here, this is a metal. What is the characteristic of this metal? As the current starts increasing through it, it causes more agitation in the material, causing more heating effect, and because of that, the resistance increases, which is basically meaning the obstruction to the flow of electric current, opposition to the flow of electric current increases. Yeah.
So, why exactly does heat increase? Is it because the atoms are like moving?
Agitated.
Okay, cool.
That's why I said the example. If you're all eating chocolate and swinging your hands left and right, and if I try to go through you, I cannot just pass through you easily. You're agitated. You're agitated, and it's not easy to pass through. Like imagine someone is giving a speech, and everyone is angry with the speaker, and there's a lot of commotion in the public. Can he just move through and reach someone sitting at the back so easily because of this agitation? It is not easy for him. He won't feel comfortable walking through. But imagine they're all enjoying the speech, and at the same time, this person actually prefers to walk and talk to someone right at the back. It will be a clean path. People respect him. So everyone is calm and he just walks through beautifully. Right? You understand what I'm saying? So when current flows through a material, agitation is caused. That agitation kind of increases the resistance. And that increase of resistance is going to deny the increase of current. Look at this. When the resistance increases, the growth of current is kind of denied. Can you see that? Look at the growth here. There's a good amount of current growth possible initially because low resistance. As the resistance increases, the current is hardly growing. The opposition is increasing. So the current is not allowed to grow that much. This is what happens in a metal. Now we have another material which goes the other way. There's another material that goes this way. This is also non-ohmic. That's also non-ohmic. Both are non-ohmic. This line is also non-ohmic. That one is also non-ohmic. As long as it's not following a straight line, it's not proportional, it's definitely non-ohmic. But this material, what is happening to the resistance? Initially the resistance is high, and the resistance gets lowered. Resistance is getting lower and lower as the current increases. That means that more and more it's causing agitation. It's letting more and more current to flow through. This is also called non-ohmic, and it is not a metal, it's a non-metal. Semiconductors, for example. So in semiconductors, like graphite, carbon, silicon, germanium, all that on the on the periodic table, which are considered kind of non-metals, that one. So what exactly is happening in a semiconductor? Why is this resistance? So in semiconductors, what do you call it? As current increases, resistance decreases. As current goes up, the resistance kind of goes down. Now we'll discuss as to why the resistance is going down. If you remember from last year, I mentioned something about semiconductors and all that last year, did I?
I think it was earlier this year.
Was it early this year?
Semiconductors at some point last year.
I don't think.
I have to get my notes in from last year. Silicon and germanium. Yeah, that was earlier. And doping.
Yes, but this year,
Yeah, that was good.
under what context did I give you that?
I don't know, but you should go again, because I'm.
That's fine, I'll go through it again.
It was like higher change resistance of semiconductors
Oh, okay.
and doping with impurities makes semiconductors more connected.
Yeah, anyway, what is a semiconductor or what is silicon? So this is like silicon, germanium, are some of the examples. So if you take a pure silicon crystal has 4 valence electrons, and in a crystal of silicon, I mean this is just one atom. In a crystal you will have bunch of silicon atoms, and they all have lots of electrons. I mean 4 valence electrons. What happens is between the silicon atoms they are all bonded by covalent bonds. So that is basically a covalent bond. So in a pure silicon crystal, at 0 Kelvin, R is infinite. That means it's an insulator. A pure silicon crystal at 0 Kelvin, R will be infinite, which means there is no conduction possible because there's no free electron. All the electrons that are around silicon atoms are all busy, occupied. They're all bonded with covalent bonds. So at 0 Kelvin, resistance is infinite. However, at room temperature, what is room temperature? At 300 Kelvin, which is room temperature, resistance will be finite. That means there will be some resistance, probably in kilo ohms, mega ohms, something like that, but it is a finite value, it's not infinite, it's not an insulator anymore. So what's happening at 300 Kelvin? Resistance is a finite value. Break up, yes. That's what happens. At 300 Kelvin, there is enough agitation that will break the covalent bonds, some of them. So some of these covalent bonds break up, releasing free electrons, and the more and more covalents are broken at higher and higher temperatures, more and more electrons are released, which will make more and more lesser and lesser resistance, which makes the current go higher and higher. Look at this. At higher currents, causes more heating. More heating reduces resistance. You can see it's flattening out. And the reduction of resistance is going to promote increase of current. Can you see that? The current is increasing. Look, this is the current axis. You can see the current is increasing for even a tiny voltage change. That is what happens in a semiconductor. So in a semiconductor, as the current increases, the temperature increases, temperature increase will reduce the resistance, and the reduction of that resistance will make the current go higher. And the current going higher will again reduce the resistance, which will make the current go further higher. It's kind of self-destroying thing. So the increase of current caused the temperature rise. Temperature rise reduced resistance. Reduction of resistance made the current go up. Reduction of resistance made the current go up, right? And that will cause more heating. That will cause resistance to drop further. That will make the current to go up further, and eventually it will just burn up. if you just let go a current through a semiconductor in that manner, it will just destroy itself. Now we don't want any semiconductor to behave in that manner. We need it to behave not based on temperature, but based on other factors. And that is why if you dope crystal with, let's say, pentavalent impurity, an impurity means something that doesn't fit into that. Okay? Like for example, in this classroom, if I bring in a student, a new student comes in, he knows only Arabic, and he's sitting in this classroom. He's an impurity as far as we're concerned, because he doesn't fit into this class. Or if someone who knows only German comes and sits here, well, that's an impurity for us again, because he doesn't fit in right because he knows only German and he can't correspond with anybody. He cannot understand what I'm saying. I cannot understand what he's saying. Therefore, everyone is going to be bothered, right? Everyone is going to be affected because of that. And that is what an impurity does. So when an impurity like boron comes in, I think boron has 5 valence electrons. If there are 5 valence electrons in boron, is it 5 or 4? It's 3. It's 3? Either 3 or 5. Arsenic and boron, I always... This is 3? Then arsenic must be the other one. Arsenic must be 5. Boron is 3. You can check it out in the periodic table. So if you bring in a pentavalent impurity such as this, what will happen is 4 of those 5 are bonded properly. There's 1 which is spread. 1 is not bonded. And that will cause extra charge carriers to exist. And that means when you apply a potential difference, these electrons will start moving. That means this is now a conductor. The more and more you dope this material, the more and more impurity atoms you put in, the more and more free electrons are going to be available. So therefore, the lesser and lesser the resistance becomes. You get it? So if I want to create a 10 ohm resistance, I just dope it a little bit and it's fine. Okay? And if I want to make it 0.001 ohms resistance, then I have to dope it a lot to make it really conduct well. Now that is one way we make resistance. So when you talk about resistors, we make those resistors purely by using semiconductors, impurity into semiconductors. We don't want the temperature dependence approach. We don't want that. That's kind of risky, because that means it will have one resistance at this temperature and another resistance at some other temperature. As far as temperature is concerned, we don't want the temperature to go up. We want to control the temperature, because even if a semiconductor is doped, temperature will be making its own effect. Because even if it is doped, to break these covalent bonds, temperature is enough. So what happens when a diode or a transistor or some electronic component or your CPU or anything like that in a computer, what will happen if that is heated up? Because they are made of semiconductors. If that is heated up, that will cause extra bonds to be broken. That will make the resistance go down, and that will make the current to go up. That will cause more heating and more current, more heating, more current. Ultimately, the heat is so much that it will just burn out. And that's why we use heat sink. All right. I think I showed you all that one, right? Last class. Heat sink. In your computers, on the processor, that is the processor is just a flat IC. On the processor, there will be a big block with a lot of fins on it. Have you seen it?
I don't know.
Don't remember. Arsenic is AS, AR will be argon. So here it is. This is basically your computer board. You can see that. These are the RAMs. These are the RAMs. You can see that. These are the RAMs. And this is the heat sink I was talking about. See? You can see how many fins it has got. And these are meant to dissipate the heat. And there's another heat sink right there. Can you see that? It is sitting on one of the processors. And some ICs which are actually supposed to be doing all the work. This is sitting under the CPUs. CPU is right under this. Now, what if this is not sitting properly? That means it is not going to suck the heat from the IC. So what will happen? The IC becomes heated, superheated, and finally just runs out. So if a computer is burning out for some reason, that is probably the cause. Anything can be enough for something to. And also sometimes your computer will start working more and more because of viruses. That can happen. There are some malwares and bugs and viruses that gets inside your computer. And what does it do? It starts running all the programs that you have on your computer at the same time. You don't want it to, but it just starts it off all. And in addition, it will bring in more programs and start it also. And so what will happen is the computer will be very busy all the time. Not even when you turn off everything, it is very busy. You can even hear the sound that's going on as the computer works. And so consequence, this thing starts getting heated up, superheated. A remedy for it, click on processes and find out what processes are on at that time. You can see it yourself, big list, all are on. And not, the same program, you'll have multiple editions of the same program running together. You didn't install it, you didn't start it, but it started itself. And if you look at the CPU's percentage used, it will be 99.9%. Right? All your memory is basically used up. So when you start a program, it will take forever for it to open. You open a Google site or something like it will take forever to kind of open up. Reason? It's very busy. So what you can do is you can shut off those programs and you can see clearly things are getting better and better. But the next time you restart the computer, it will automatically come back again. Those are things that can actually mess up with this. So there are those viruses and all that. Sometimes I feel like those viruses are actually brought in by the antivirus company itself. Because earlier I had a Toshiba before, and that Toshiba, I was very concerned, so I took Norton antivirus, and then after 1 year, immediately it started telling me, oh, it's out of date now, so you need to purchase, whatever. So as that started happening, I could see that infections are also coming in immediately. It started bothering me to that extent. I said, okay, now I don't want to buy anything. Let me just reformat the computer, clean it up to factory settings. And once I reset everything to factory settings, saving what was needed, it was again a brand new computer. And then again I go and download some antivirus, AVG, and say, I'm thinking to myself, AVG is wonderful, so it should be taking care of it. Yes, it is taking care of it for some time, and after that, before the thing expires, it starts sneaking in stuff. And then slowly I can see the computer is actually infected with all these viruses. Result, before the end of the year, I'm like bothered so much, reformat it. I did this thing for many years at a stretch. And finally I was so fed up that I reformatted it and said, bye-bye to antivirus. I'm not going to download any antivirus. Let it run without antivirus. And guess what? Nothing happened after that. It was all clean. Nothing was happening. Of course, I don't go to useless sites and click here and there. If someone sends an email, I will be is it something that is genuine from that person? I may even call that person and say, did you send that, or it was just okay, delete it. Okay, so you should be able to figure out, is that email something that is genuine or not? All that matters for you is just click somewhere and then read out. And they have control of your computer. So once I kind of said, no more antivirus, I was doing my banking and all those things perfectly well. There was not a single virus that was getting in. So I used the same Toshiba until it started failing in multiple other ways mechanically. Mechanically started failing, the screen went off, and then I had to replace the screen. So I started thinking about another computer, then I went for the Mac. It's been there doing its work superbly. It's doing a wonderful job. I have not had any botheration with this computer. I don't care, about where I'm going. Everything is safe. So that is a wonderful machine. Initially, I was hesitant to buy a Mac because I was thinking, I don't like the idea of turning something off from here, and turning, all those things. I didn't like that idea, and also the SPAD, moving 5 fingers and 4 fingers and all those things. But my son actually said, you should go for it and you'll like it. Because I was thinking, like, what about programs? I have to download this, WinZip, and I want to do all these things. And I was thinking that this one cannot do it and so on, but everything is there for this machine. It's doing everything. My favorites are GarageBands and iMovies and all those things. Now I'm able to put these videos up, edit it at the right time and right place, and insert something else or slides or whatever I want to do. Everything is not, easy for me to do on this one. GarageBand, yes, plenty of help. If you don't control on the temperature, then it can actually go this way. All right, clear? So ohmic conductor, non-ohmic conductors. So if you're asked, like, explain why the resistance of a metal increases and the resistance of a semiconductor decreases when current is made to flow through them. What do you say? What do you say? Yeah, in metals, when the current flows through it, it causes the atoms to get agitated, which will cause more obstruction to the flowing electrons, thereby the resistance goes up. And in a semiconductor, when the agitation is created by the flowing current, the agitation makes some of the covalent bonds break, thereby releasing free electrons and thereby creating lesser resistance. So that's what you should be actually saying. The other things that you have probably again done is resistivity. What is resistivity? Have you seen it before? Yeah. So if I'm taking any material, the resistance of that material is directly proportional to the length of the material, correct? And the resistance of the material is also inversely proportional to the area of the material. So if a material is longer, it will have more resistance, like this. So if this resistance is R, this will be R. It's proportional to the length. And is inversely proportional to the area of cross-section, which means if it's this wire of a certain length, as the resistance is R, and the area is A, keeping the same length, if the area is bigger,
It's going to be smaller. The resistance is going to be smaller.
the resistance is going to go smaller. Okay? So here the resistance is going to go smaller when the area is going to get bigger because it was proportional. And R is proportional together with A and L. And R is equal to a constant of proportionality times length over area. This constant of proportionality is called resistivity or specific resistance. It's called resistivity or specific resistance. Now if I pull out the resistivity from here, I get resistivity is equal to RA over L. And that will let us know what is the unit of resistivity. What's the unit of resistivity? R has a unit of ohm, A is meter squared, and L is meter. So what's the unit of resistivity? Ohm meter. You can write it that way, or you can write OHM and then dash M. You can also write it as ohm meter. So the resistivity has a unit of ohm meter. And resistance is dependent on the material. Okay, resistance is a characteristic of the material. Resistivity is a characteristic of the material. Now, if you take the reciprocal of this, you take the reciprocal of this equation, you get 1 over R is equal to 1 over rho L over A. And this 1 over R is called conductance. Some books write it as G, conductance. I don't know where the G came from. But conductance is equal to 1 over resistivity is called conductivity, sigma, and then L over A. So what is that symbol? That's called conductivity. It is just the reciprocal. So if R is resistance, what is resistance? The amount of difficulty, right? And conductance means how easily it's made to conduct. So it is just the reciprocal. Conductivity is the inverse. So resistivity tells you like how much resistance it can offer. Whereas this one says how much conductance can it offer. Like how much conductance, so conductivity. So what is resistivity actually? Resistivity is the resistance of a material whose area is 1 meter square and the length of the material is 1 meter. If you put 1 meter square for area and if you put 1 meter for the length, you have resistance, and that is resistivity. Like if I take a cube, and the side of the cube is 1 meter, and if I attach probes to this side and this side of the cube, you know what I'm saying? So if you have a cube, not a cuboid, but a cube, imagine the sides are 1 meter each. And if I take the probes and connect it like that, what resistance am I going to get? That is resistivity. Why? Because what's the area of this? And what's the length of that? So if the area is 1 meter square and length is 1 meter, resistance is the resistivity. Or resistance is the resistivity. Or whatever it is. So if you check the resistance across the opposite faces of a cube of side 1 meter, what you're getting is the resistivity. Make sense? So if you're checking the opposite faces of a cube of side 1 meter, the resistance you're getting there is the resistivity. Talking about units. Conductance has a unit which is ohm minus 1. But instead of writing ohm minus 1, is also written as anything funny there? It's backwards. That's it. Mho. This is ohm written backwards. That is a unit of conductance. Mho. And if it is a very small one, it's millimho and all that. Micromho. Okay? This is the conductance unit mho. Now, so this again, resistivity's unit, is ohm minus 1. So sigma is conductivity, whose unit is ohm minus 1, meter minus 1, or you can call it mho, meter minus 1. Okay? You can write it any way you want. That's what it is. Questions? Let's give you a quick question. Suppose there's a copper wire like this. And there's another copper wire like that. Which one has more resistivity? Which one has more resistivity? The top or the bottom? You know, when I ask, there's always a trick behind it. What? It's the same. It's copper. I told you, resistivity is a characteristic of a material. Copper has one value of rho. Gold has another value of rho. It's all unique. Get it? Yeah, this one has more resistance compared to this. Obviously longer and thinner. This is shorter and fatter. So therefore, this is definitely a smaller resistance compared to that. But resistivity depends on the material. So if the material is exactly the same, you can just say it's a common thing. Temperature coefficient of resistance. Temperature coefficient of resistance. What is the temperature coefficient of resistance? You know that the resistance of a material will change when the temperature changes, right? So when the temperature changes, resistance will change. And how much it changes by? Per ohm, per degree rise in temperature. That is called temperature coefficient of resistance. And the symbol that is used is alpha. Symbol used there is alpha. Alpha represents temperature coefficient of resistance. To understand that better, let's say you have a material. And at a certain temperature, the resistance of this material is 1 ohm. When the temperature goes up by 1 Celsius, how much does the resistance change? That is alpha. Okay? Now putting it all into a table format to understand everything, this is resistance. That's the temperature change. That is change in resistance.